Today we are going to discuss about the concept of duality. What is dual, what is primal of a linear programming problem, and when we will identify that one is primal, then how to get the dual linear programming problem and why that came into picture, what is the motivation of that. So that we are going to discuss in today's class, along with some example problems, how to convert from primal to dual. Those things we are going to discuss. So first we will see in motivation why we need that thing, what is the idea. So in simplex method, if you remember, okay, simplex method for LPP, so there will be two type of problem. One is maximization, another is minimization problem. Whether you take maximization problem or minimization problem, in simplex method we have to construct the simplex table and we have to proceed. When we have to stop, when Cj, capital Cj, if you remember, capital Cj is less than equal to 0 for maximum case, then we stop the process and we can identify what is the optimal solution. Similarly, in minimum or minimization problem, we find out C capital Cj is greater than equal to 0. So this is the basic concept. And another thing what we have, if we have maximum z, that we can write it as minimum of minus z. In that way we can write, but the complication occurs when you have maximization problem and you have the constraints are like greater than equal to or equal to, then the problem occur. When you have minimization type and you are getting the constants as less than equal to or equal to, so that type of problems occur. So how to deal with that problem? Okay, so those are the major challenges we had in simplex method. So here little different concept we will see. So one LPP will have two different problem here, maximization and minimization, or we can say that in terms of a single word, if you see, that is called duality. So the concept of duality comes from here. Okay, that one LPP will possess two type of problem. One is called primal, another is called dual. So those two type of problems are there, and how they are interchangeable means how, if primal is given, then how to get dual, dual is given, how to get primal. So that we are going to see, means only we are going to see the canonical form of primal is given, then how to find out canonical form of dual. We are not going to discuss about standard form, because any one of the form we know we can convert into standard form and we can start simplex method, start doing. Okay, so at the end we will see the solution. What will be the solution of primal and dual, means whether they are same or not, or what sense they are same. Okay, feasible solution, unbounded solution, so those things. So let us start the motivation in detail. Okay, so one of the most interesting concept in linear programming problem is duality theory. So every linear programming problem has associated with it another linear programming problem involving the same data. That means if we have a problem, LPP is a problem given, the data will be same, but there will be two type of LPP involved in one single LPP. Okay, and the closely related to optimal solution. Such two problems are and add to be dual of each other. Like we say complement of each other, similarly it will be dual of each other. So while one of these is called primal, one problem is called primal and another problem is called dual. That's why we say these are dual to each other. Next is that if the primal contains large number of constraints, so this is one benefit here we are going to discuss. So if the primal contains a large number of constraints, and a smaller number of variables. That means if we have the case m is greater than n, understand, if number of constants are greater than the number of decision variables, the labor of computation can be considerably reduced by converting it into dual problem and then solving it. Here you see, if any problem is given, think that we have very less number of decision variable, the constants are too big. Too big means many constants are there, large number of constants are there. Then what to do? If you prepare the simplex table, you have to do lot of row operations. Okay, so if you want to avoid that, then what you can do, you can convert that problem to dual problem. Means you can get another LPP from that LPP using the same data. How to do those things we are going to discuss in the next. Okay, but here you can see the labor of computation can be considerably reduced by converting into a dual problem. So if you change it to dual problem, what happens, you had their body matrix. Okay, so body matrix consists of the x variables, okay, the columns of x variables and the coefficient of x actually from the constants. So dual problem, we take the transpose of body matrix. So that's why the row becomes column, column becomes row. That's why the computation will be reduced. So that is another benefit of using the duality concept. So the interpretation of dual variables from the cost or economic point of view proves extremely useful in making future decisions in the activities being programmed. Okay, so these are the motivation. Next we will learn how to formulate the dual problem. Okay, so these are very important points, carefully observe. So one by one we will discuss. The maximization problem in the primal becomes minimization problem in the dual, vice versa. So if in primal we have maximization problem, then dual becomes minimization problem. So within LPP we have one maximization problem, one minimization problem. Understood? If initially it is given maximization problem, then its dual will be minimization problem. If initially it is given minimization problem, then its dual will be maximization problem. Understand? Now the less than or greater than equal inequalities type, okay, less than inequality type of constraint in primal becomes greater than. Okay, like if you are dealing with maximization problem and you have greater than equal to type of constants, so it will convert into minimization problem and less than type constants. Okay, so that very important. If the constants are provided less than, then its dual constants will be greater than type. Okay, or vice versa. Next thing is that the coefficient C1, C2, Cn. So when we have the problem like maximize z equal to how, C1 x1 plus C2 x2 plus C3 x3, like the problem is given. Now what happens, this and subject to the constant, how we have to write the constant, you see, let it be s1. Okay, s1 is a11 x1 plus a12 x2. Okay, like that, let it be less than equal to maybe b1. Okay, similarly s2 s3 you can get. So what happened, the coefficient of c1 c2 c3 c4 cn, okay, in the objective function of the primal, if this is the primal problem, in the primal problem it is given, okay, this c1 c2 c3 will become this b1 b2 b3 in case of dual. Okay, you see the coefficient of c1 c2 cn will be b1 b2 b3 bm in objective function of the dual. We will see through example, then it will be more clear, you can visualize nicely. Now the next one is the constraints. The constraints, what is b1, b2, b3, whatever bm is there. So b1, b2, b3, bm in the constraints of the primal become the c1, c2 dot 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 cn in the constraints of the dual. Okay, so if next is if the primal has n variables and m constraints, the dual will have m variables and n constraints. Just it will be transpose. That is the transpose of the body matrix of the primal problems gives the body matrix of dual problem. Okay, if you remember, then you can visualize the thing. Now when you are going to discuss about the problem or example, then it will be crystal clear. So the variables in both the primal and dual are non-negative. So non-negative condition is satisfied. The last condition is always will be there. So for both primal and dual, all the variables whatever involved in there, it should obey the non-negativity condition, means greater than equal to 0. Okay. So next we are trying to see from the general or generalized notation. So consider the LPP maximize z equal to c1x1 plus c2x2 plus and so on plus cnxn. So this is the objective function subject to the constraints a11x1 plus a12x2 plus and so on plus a1nxn is less than equal to b1. Next a21x1 plus a22x2 plus and so on plus a2nxn is less than equal to b2 and so on. The last equation will be am1x1 plus a m2x2 plus and so on plus amn(xn) is less than equal to bm, where the non-negativity condition is that x1, x2 and so on up to xn greater than equal to 0. Okay, so this is our primal problem. Now from this we will get the another LPP, that is called dual. Okay, so how to do? So first thing is that maximization. So maximization will change into minimization type. Accordingly this z will also change. Understand, this is the first point. Second thing is that this less than equal to inequalities are there. So this inequalities become greater than equal to. Okay, done. After that you can see this c1, c2 and cn, these are the coefficient of objective function. So this will come here actually. This will come here. This will be considered as b1, b2, b3, bn for duality problem, and this b1, b2, b3, bm of this primal will be considered as b1, b2, b3 up to bm for the objective function. And the body matrix, the coefficients are a11, a12, a1n. So those will be what? Transpose, means a11, a12, a13, like that, a1n, a21, a22, a23 and so on, a2n, and like this, am1, am2, am3 and so on, amn. So those things are there. So this matrix we have to take the transpose. Okay, and this x1, x2, x3, xn variable will be replaced by other notated values, variables. Okay, and it will satisfy the non-negativity condition. So let us see if we apply those things, then the final form how it looks like. Okay, so the first one, maximization, is changes to minimization type, and z, the variable, we will write other variable, we will not write z, we will write any other notation there, it is possible, except z. So somewhere you can write w, somewhere z dash, it's fine, no problem. You see, after that what, here b1, b2, b3, bm are there, yes or no? So those are considered as the coefficient. So b1 y1 plus b2 y2 plus and so on plus bm ym, fine. Now this c1, c2, c3, the coefficient from the objective function of primal problem will be the b1, b2, b3 value in dual problem, you see here, and the sign changed, greater than equal to, greater than equal to, greater than equal to, c1 here, c2, like that, cn. If you see how many variables are there, m variables, how many constants are there, n constants, but primal, how many variables are there, n variables, how many constants are there, m constants are there, okay. Now the body matrix also change, you see, a11 x1 is there, okay, so a11 a1 is there. Now a12 x2 is there, but here it will be a21 y2, that means this way it is going column wise, a11 y1, a21 y2, then and so on, a m1 ym, like that you have to write, a12 y1, a22 a22 y2, and so on, a2m ym is greater than equal to c2, like that. The last row, am1 x1 is there, am2 x2 is there, and like that. So here it will be what, a1 n y1, this one, then a2n y2, this one. So we are taking the transpose, if you see, plus and so on, plus a mn y here ym, okay. So it will be a mn is there, so a mn ym is considered. Now understand the concept, and the non-negativity condition will become y1 y2 and so on, and ym greater than equal to 0, okay. So in this way you can convert a primal problem to dual problem. So whatever the problem is given, we consider that as it is as the primal problem, okay. From there we consider or we extract the dual problem like this. So imagine here, if you have m number of constants and m is too large, okay, if m is too large than n, then what happens, you have to do lot of table calculation. But if you change into this dual problem, what happens in this problem, what happens in this problem, n will become less than equal to, or same thing will be there, but where m variables are more than n variables are less, okay. So those things are there, then it will be easy to calculate, easy to find out the optimal solution, okay. So next we are going to see one example problem which will give you complete idea. So to construct the dual of the following problem, that means this is the primal problem, okay, we have to find out the dual of this. So it is a maximization problem, maximize z equal to here 3x1 plus 5x2, this is the c1 value, this is c2 value 5. So c1 is 3, c2 is 5, clear. Now subject to the constants, this minus x1 plus 2x2 less than equal to 2, so this is 2 is b1, x1 plus 3x2 is less than equal to 4, this is b2 4, x1 is less than equal to 3, so b3 is 3. Now here from this constant, if you want to see the coefficients, so a11 coefficient is -1, a12 coefficient is 2. Then A21 coefficient is 1. A22 coefficient is 3. Then A31 coefficient is 1 because x1 is there but there is no x2. So A32 coefficient, this value is 0. Okay, so now we are in a position to convert this primal problem to dual problem. So how we will do that? Let us see. So maximize will be minimize, and we have written minimize z dash. So you have to write any notation except z, otherwise it will be a confusion. So minimize z dash equal to what? It will be, it should be b1 y1 plus b2 y2 plus b3 y3, yes or no? That means b1 is 2, that's why 2y1 plus b2 is 4, that's why 4y2 plus b3 is 3, so 3y2. Done. Objective function part is done. After that we have to construct the constants. Okay, so constant, how it will be? You see, we have to take the transpose of that. So if this is the coefficient, then transpose is what? This you have to take. Okay, this. So A11 is -1, that's why -1 into y. Okay, done. Then A21 is 1, so 1 into y2, so y2. Then A31 is 1, so 1 into y3. So minus y1 plus y2 plus y3 is greater than equal to, because less than equal to was there, so it will be greater than equal to, then it will be C1. So C1 is 3 here in the problem. Now next one is similarly this we have to see. So like this we have to do. So 2, first is 2, so 2y1, then 3 into y2, so 3y2, so 2y1 plus 3y2 plus 0 into y3, so no need to write, is greater than equal to C2 value, that is 5. So 2y1 plus 3y2 is greater than equal to 5. Okay, fine. Then what are the variables? y1, y2. So y1, y2 greater than equal to 0. And this is the extra variable. Okay, you can write like this. So it's clear, I hope. So if it's clear, then we will see the, so next section is the formulation of dual problem when primal has equality constraint. So it is also very important. Till now we have seen the standard one. Now think about equality is there, what to do. So let us see the primal problem, this maximize z equal to c1 x1 plus c2 x2 subject to a11 x1 plus a12 x2 equal to b1, and a21 x1 plus a22 x2 is less than equal to b2. Here equality is there, and the non-negativity constraints or non-negativity condition is there, x1 and x2 greater than equal to 0. Now this equality how we will handle? If we have a equation a11 x1 plus a12 x2 is equal to b1, so we can write like this, a11 x1 plus a12 x2 is less than equal to 1, and a11 x1 plus a12 x2 is greater than equal to 1. We can write like this, or we can convert in this way, like both we have to write. If we have to write both as less than equality form, then the second equation, this one, or second inequality, this, if I multiply -1 both the side, it will convert it into this. So minus a11 x1 minus a12 x2 is less than equal to minus b1. Done. Now this we have to incorporate properly and find out the dual. So here dual will be maximized, z was given. So okay, first we have to write the changes which we have done in the primal problem, then we will do the dual problem. So in primal problem what we had and what will be the change, you will see. So the changes will be here in constraint. Okay, So instead of two constants we had, here we have three constants with inequality sign, because equality sign was there in the problem. So what will be that a11 x1 plus a12 x2 is less than equal to b1. Then next is this one, the second change we have done, minus a11 x1 minus a12 x2 is less than equal to minus b1. Then the third one, which is as it is same, we have to write a21 x1 plus a22 x2 is less than equal to b2, where x1 and x2 greater than equal to 0. Done. So if this is done, next part is that we have to convert this problem to duality. So how to do? Let us see. Here the deviation is there, okay, this two equation, so we have to carefully observe this. So we will write the minimization W will be here. You see how many value are there here, b1 and b2, two values are there. So this two value will be used for writing the objective function in the duality. So b1 y1, b2 y2, but here three equations are there. So how to write that? So we can write that b1 y1 dash minus y1 double dash plus b2 y2. So we have to replace this y1 as y1 dash minus y1 double dash. Then it will become subject to the constant will be what? a11 into y1 dash minus y1 double dash plus a21 y2 greater than equal to c1. Similar way we have to proceed, and the last one will be very simple, a12 into y1 dash minus y1 double dash, okay, plus a22 y2 is greater than equal to c2. And what are the variable you are getting here? y1 dash, y1 double dash, y2 greater than 0. I hope it is clear. So if it is done, then this also we can write in simplified form as this. Here, from here, what we understand that y is unrestricted, that's why we have used this y1 dash and y2 dash variables to express y1. So that we can write, so minimize w equal to b1 y1 plus b2 y2 subject to a11 y1 plus a21 y2 greater than equal to c1, a12 y1 plus a22 y2 is greater than equal to c2, where y1 is unrestricted in sign, okay, and y2 is greater than equal to 0. So this way we can convert. After converting this way, you can apply the simplex table if you want to solve the problem. But the conversion from primal to dual is this way. And if it involves equality, so we have to follow this procedure. So think about, you have m equalities, okay. In the constant you have m constants and all are equality form. So how to do? That means m variables you have to take as unrestricted in sign. So that's why this maximization problem is converted to minimization problem, minimize w, and the modified form of the constants is like this, and last you can see y1, y2 and so on, ym all are unrestricted in sign, okay. So this way you can convert. I hope you understood this concept. If you understood this concept, then we have to see the example problem. Here the example problem is given, maximize z equal to 3x1 plus 8x2 plus 5x3. So 3 is c1 value, 8 is c2 value, 5 is c3 value, subject to 2x1 plus 3x2 plus 2x3 is less than equal to 9. So 9 is b1 value, 3x1 minus 2x2 plus 4x3 equal to 7. So 7 is b2 value. So b1, b2 we know, but here one equality is there. So if equality is there, unrestricted variable will come, and x1 and x2 x3 greater than equal to 0. So maximization will become minimization. So minimize z dash. So z dash here we have used the notation, except z you have to use, okay, whatever variable. So minimize z dash equal to this 9 is b1, so b1 y1 9 y1 plus b2 y2 7 y2, done. Okay, so after that, subject to the constants now how it will be. So 2x1 is there, so 2y1 plus 3x1 is there, so 3y2, so 2y1 plus 3y2, and the less than equal to will change to greater than equal to, so greater than equal to c1 value is 3. Now similarly next one is 3x2 is there, so 3y1 we have to write, minus 2x2 is there, so minus 2y2 we have to write. So 3y1 minus 2y2 is greater than equal to c2 value, c2 is 8. So 3y1 minus 2y2 is greater than equal to 8. Similarly last one from here, the problem 2 is there, 2y1 plus 4y2. So 2y1 plus 4y2 is greater than equal to what? 5, because 5 is the C3 value. Now here you can observe that in the second equation, what is there? Second equation equality is there, yes or no? So if the second equation equality is there in the problem and that corresponds to B2, so B2 will be multiplied with what? Y2. So y2 will be unrestricted, that's why. And y1 greater than equal to 0, and y2 is unrestricted in sign. So it will be done. I hope it is clear from problem point of view also. Next we will see the duality principle, which will be very important, and this is the last part of this talk. So if the primal and dual problems have feasible solution, remember here, if you are extracting dual problem from the primal problem and you are solving those things, those two problems, and see that both have feasible solution, then what we have? Then both have optimal solution, and the optimal value of the optimal value of the primal objective is equal to the optimal value of the dual objective function. That means if your primal and dual problem, okay, in that problem if your decision variable satisfy the constraints, then it has feasible solution. So if they have feasible solution, they have optimal solution, and if they have optimal solution for both primal and dual, both the problem, the solution or the optimal value of the objective function will be same. Okay, so this is the duality principle, and this is nothing but our fundamental theorem of duality. Understand? So maximize z equal to minimize w we are getting. So this is the primal problem, this is a dual problem. What about the solution? Solution is same. So this is nothing but the fundamental theorem of duality. It suggests that an optimal solution of the primal problem can directly be obtained from that of the dual problem and vice versa. So if you are finding the primal problem and it is feasible solution, then using this theorem statement you can tell that the dual problem will have also same optimal solution. Okay. Now we will see what is the working rule for obtaining an optimal solution to be primal problem from that of the dual, okay, or dual to primal. Okay, what is the working rule that we are going to see and discuss? Suppose we have already found an optimal solution to the dual problem by the simplex method or primal problem by the simplex method. Understand here, any one of the problem you have found out the optimal solution from the simplex table or by using simplex method, you have found out any one of the problem's solution, primal or dual, then what happens? Rule 1 is if the primal variable correspond to a slack starting variable in the dual problem, then its optimal value is directly given by the coefficient of slack variable with the changed sign in Cj row of the optimal dual simplex table and vice versa. For example, if you have table like that, so in the table you have basis. In basis you have, let it be slack variable s1. So s1 is having some value here, maybe in the optimal table. Let s1 you are having 5. Then you are solving the primal problem. So in dual problem it will be -5. The solution will be considered -5. So if the primal variable correspond to a slack starting variable in the dual problem, then its optimal value is directly given by the coefficient of the slack variable, okay, with the changed sign. Means 5 is there, so it will be -5 in the Cj row of the optimal value, optimal dual simplex table and vice versa. So this will be more clear in the next class when we are going to discuss about dual simplex method. So this rule will be useful. So first you understand the rule. Then next rule is that if artificial variable will be there, means if the primal variable correspond to an artificial variable, means this is big M method, like is there big M method plus M minus M we are using, and artificial variable we are using. So in that context, okay, if the primal variable correspond to an artificial variable in the dual problem, then its optimal value is directly given by the coefficient of the artificial variable. Similarly, we have to do with changed sign, means if A is there 5, it will be -5. Cj row of the optimal dual simplex table after deleting the constant M and vice versa. So this will be more clear once we understand dual simplex method, which will be discussed in the next class. So if we summarize everything, so what we will get, that on the other hand, if primal has an unbounded solution, means whatever problem you have, if you treat as primal problem and it has unbounded solution. When we are getting unbounded solution in simplex method, if you remember, then tell me, when you are not able to find out the key row, that means the ratio. So key row, if you are not finding out, then we can say, if you are not getting, after finding key column, if you are not able to find out key row, then we conclude that unbounded solution is there. Then what we can say, if the primal has unbounded solution, then the dual problem will not have a feasible solution, or and vice versa. Vice versa means if your primal is having and not a feasible solution, that means dual is unbounded. Primal unbounded, dual infeasible, okay, then dual unbounded, primal infeasible, okay. So that concept, I hope the concepts are clear to all of you.